and it just said that I finally posted scores. I figured out how to put a non-WebAssign assignment into WebAssign so that you can see what you actually got. And I apologize because I did not want it to be that long, but they are there now. And in that vein, I also have noticed that I can see whenever one of you view an answer key to the homework. And relatively few of you actually have ever looked at any of the answer keys. I can't make you. I'm a little curious why you're not curious what the actual answers are, but the point is they're there. You can view them. I strongly suggest it. Do with that as you want. You're adults. And nobody's asked before, but I definitely have the bubble sheets. If you want your bubble sheet from the exam, you can come find it. You can do that now if you want, or after class if you think it's easier. Well, it won't disturb me anyway. And the homework on chapter 6 and 7. Let's see, today's Wednesday. All right, we'll be starting chapter 7 with energy and getting most of the way through it Friday. If I don't get through anything, we'll finish up on Monday. I hope to get to the projectile motion in chapter 10, just the projectile motion part in chapter 10 Monday. The homework that is then due Monday at midnight, I believe is what I have set. Unless we get really stuck, I'll bump it to Wednesday, but that's the plan. Correct. Is not in the homework. Yeah, I want to cover it so you don't feel crammed like you have to understand it in a half a day. So that will be on the next homework, chapter 10, along with 13 and 14 is the plan. But just so you remember, homework is due Monday, lest you haven't bothered starting. And I don't have the question on me, but somebody wanted me to discuss a little the tug-of-war question at the end of the exam. Is that the right one?
Yes.
It was the big strong man and, Susie, little Susie pulling on the rope. And since I don't have it in front of me, what did I ask? Was it who pulls harder? Are they the same on the rope?
Yeah, that's what got me confused because I was thinking that the action-reaction pair was each separate person on the rope, and I wasn't thinking the action-reaction pair was the big guy and the little girl.
Gotcha. So he said narrowing down the action-reaction pairs versus who's actually pulling on the rope confused him a little. And that one, you noticed I asked several action-reaction pair questions. That one was after a couple others. And because it was involved several action-reaction pairs. So the fact that you realized lots was going on was my intent. So if we narrow it down, Arnold, that's who it was, the strong man pulled on the rope. The rope pulled back. That's an action-reaction pair. And then Susie pulls on the rope pulls back. That's an action-reaction pair. Another pair that's going on is if you look at the tension in the rope. It's getting pulled one way. The reaction is it gets pulled the opposite way. If you look at tension, say you put a spring scale right in the middle of the rope, you can measure the tension because it's getting pulled this way and this way. And so we wanted you to compare, Arnold pulling on the rope versus Susie pulling on the rope, and they were the same. But it was still because of Newton's third law. If he pulls on the rope pulls on him the same, so that the tension over there is something. Same game over here with Susie, but since it's the same rope, it's the same tension. And so they're all the same force. Sure, Arnold's going to win, yes. But the force they have to resist is the same. The rope, if you want to think of it, the rope can just translate Arnold's force. He pulls on the rope pulls back. But that's the force then that Susie's trying to hold back. And she can pull. And they only pull, they react to that action. And they can only, to make it probably where the confusing part is, she can only pull as much as he pulls. And he can only pull as much as she pulls. So they were the same. Did that help? No. No. That's fair. If you do, if it doesn't, if you don't, you still don't have it.
I get what you're saying, but at the same time, it still doesn't make sense.
Anybody want to attempt to answer why he wins?
That's inertia.
I'm not an artist. Ultimately, well, that was good. If you remember in the text, the only thing that really works in a tug of war is the force between your foot and the floor. Because you can grab on here, but if you can't hold your position, it doesn't matter. And so in reality, there's action-reaction pairs going on at each of their feet too. I didn't want to muddy the waters too much. And he can still win because he can pull at a certain force, she can pull at a certain force. That's an action-react, well, this action-reaction, but it's the same tension, so they're the same force. So we have F and F, opposite directions. The net force is zero, can be zero, is zero. But that doesn't mean they can't be moving. They're just not accelerating. And so you hang the little flag here, and the flag can be moving at a constant velocity, not accelerating, and that's why he can win. He must be exerting more force here than she is here, but not on the rope. Yes?
Okay, I thought you were going to say that made sense, and maybe that there's more gravity pull on him because of his mass.
He does have more mass, so there is a greater gravity pull on him, correct? That's the Earth pulling on him. Same game over here, but that doesn't determine who wins. Oh, you look at her inertia. Yeah, she has less mass. So for this force, yeah, she has smaller mass. So it's easier to accelerate her, get her moving with that force than him. And that does come into play too. The bigger somebody is, the harder it is going to get them to move with the same force. Absolutely.
Explain again about the velocity.
I was just trying to relate it back to the first chapters. The forces are the same, but in opposite directions, which means the net force is zero. You with me? That means there's no acceleration, no change in velocity. Does not mean that there isn't a velocity. The system can be moving, most likely this way, but it's not changing its velocity. So this whole system shifts this way and he wins. But that doesn't mean he has to pull any harder than her on the rope. Yeah, part of the reason these forces balance is because of that inertia thing as well, yes. But the key to understanding why he wins, but why the forces are the same, are what I just said. Are we helping yet? Is it any clearer? Sir on the front row? Little? Okay. Let me know though, I'll keep working on it. Let that one sink in. Ask me some other time. Okay. I also felt really bad after last class, so I need to apologize to you. I tried to pull a funny. It obviously was not funny, and then it actually caused confusion, and I made a mistake. I'm wrong. It was one of those clicker questions, and you guys seemed kind of dead. I thought we just explained it, so it'd be funny if I told you the wrong answer. You guys didn't like that. I am totally sorry. I won't do that again. Okay. I wanted to go back to the air track and do some more of those since it was right at the end, and put some more numbers to it if we can sometimes. They don't have to be real numbers, but we'll use some numbers to see this conservation of momentum better. I think you guys are at least, you're getting, you might not feel perfect with impulse and momentum yet, but where it actually comes into play, I think a lot is in conservation of momentum. So we're going to do some collisions and it should review some of that, and we'll see how we do. So let's see. First one I want to do is, let's do this one. I have two carts. They're tied together. And I'm going to burn the string. They're supposed to be, well, they're about the same mass. For our intents and purposes, they're the same mass. They're squished together with a spring in between. When I burn the string, what do you expect to happen? And I guess we don't need that while we talk. The spring's tension will release, so it's going to exert a force on both of them. How do you think the force will compare on one versus the other? Yeah, the spring's going to push on this one, it'll push back, it's going to push on this one, but it's the same spring. So yeah, they're going to receive the same force. Now what? What was that? Yeah. Good. From Newton's second law. F equals ma. Yeah, if they're the same force and the same mass, they should accelerate the same. That means they'll change their velocity. What's their velocity now? So they'll get up to some velocity we'll call v. So yeah, okay, you expect them to be going about the same speed. I'm roughly in the middle here, so one way we can gauge that is if they hit the ends at about the same time. Now in terms of momentum, what's this guy's momentum now? Yeah, mass times velocity, inertia in motion, no velocity, no momentum. This guy? Total net momentum of the whole system? Good. So as they're moving apart, what will this guy's momentum be? It'll increase. What? M, because momentum is mass in motion. So it'll be mv. This guy will go from 0 to mv that way. What will this guy do? 0 to opposite mv. How will this mv compare to that mv? Same magnitude, because they're the same mass. What's the total momentum while they're in motion? 0. mv one way, but mv the other, they cancel. The total is still 0. Let's try it. Let's see if I'm pulling your leg. They look about the same speed to me. Chink. And they come back, and if they're going the same speed, right about in the middle. Very good. Very good. Now, let's make it inelastic. I have two things of Velcro. I'm going to need somebody's assistant for a moment, though, because I got to tie this string, and it only works with 4 hands. So if somebody would come up and help me just hold the carts together, we'll try the exact same thing with an inelastic collision. Thanks. Okay, we'll get that one there, squish them together. Great, don't move. While I implore my Boy Scout skills.
Yeah, that was always the one I never learned.
Knots? Wait. And okay, thank you very much. So same idea, but when they come back together, they'll stick, and we'll have an inelastic collision. What will happen when they collide? Options I can think of, they could move this way. They could not move. They could move this way. What do you think? Who thinks it'll move this way? Who thinks it'll move that way? Who thinks it'll stay put? Most of you. Let's try it. Boing. You're right. Very good. Very good. And that's true because they have the same what? The same velocity. And they acquire the same velocity because Same mass. Same force on the same mass, same change in velocity, get up to the same speed, and or they have the same mass, so they're going to acquire the same momentum change. What provides that momentum change? What allows them to go from zero momentum up to mv? Yeah, the spring exerts a force for a certain time. We call that impulse. Force for a time causes a change in momentum. Good. Okay. Hey, let's do that again. Even with the spring. I like the spring. We'll do it this way. Start thinking what will happen. I got to tie this one together though. I've never done this one in real life. This will be fun. This is about, consider this half the mass of this guy. Thanks. You're a pro now. All right. Hopefully this will stay together before I burn the string. One more. Are you predicting? Okay, let go. Let's see. Good. Thank you. First of all, as soon as I burn the string, will something be different? I heard one will accelerate faster. Which one? Yeah, so I expect this guy to be moving faster than this guy. How much faster? Yeah, a factor of 2. I expect this to go, let's say this guy is going to end up going V. I expect this guy to be going V, or 2V. And that's because the ratio of the mass is half. And then when they come back together, they're going to stick. And they're going to have their combined mass trying to move as a system. Will it go that way, or stop? Also think about, will they come back together in the middle? Where do you expect them to come back? Farther this way, because he's moving faster? So they might collide over here, but then will they stop, keep going that way or that way? Oh, boo. Friction. Wah, wah, wah. I can't see what's rubbing on this guy, but something clearly is rubbing. Talk amongst yourselves. We're on again.
Not again.
Thank you very much. Squish. That's what I'm hoping doesn't happen, yeah. It should be the same, but not yet.
As this was pulling up too much, and that's why it went up.
Well, that's my other theory, but this was rubbing also. If this doesn't work, my other theory is because this guy's more massive than that guy, this guy's getting torqued and rubbing that way, but we'll try it anyway. Yeah. Oh yeah. Zippy. Hey, we got the first part of the collision working. Close enough. That's what I wanted to show anyway. If this guy's going kind of fast and this guy's not going quite as fast when they come, he's more massive, he kind of wins. Good, now I have something to work on. Perfect that demo. Let's do just this. We'll simplify. Big mass coming at V, and little mass coming at 2V. If I'm doing a vector, do it like that. So we're just going to start there, coming out. What's the total momentum before this collision? We'll say to the right's positive. Then that guy has to be negative. Add a negative. Big M, V. I'm going to simplify. This mass is twice that mass. That's why I need to perfect. Some of you seen the problem with this yet? That's why I need to perfect this demo. What does that equal? 0. So the total momentum before the collision is 0. I hope that makes sense, because when they started, the total was 0, right? They're moving now, but the total is still 0. So when they come back together, what do you expect the total momentum to be? 0. Yeah, so ideally, if it didn't get stuck on the bottom when they come back, they're going to collide, and their total momentum has to be 0. After the collision, we have little m stuck to big M, and we'll just jump right to that. Their total momentum is going to be 2m plus m, that's the combined mass, times some new velocity. And the only way the total can be 0 is if they don't move. So ideally, when they come back together, it would still stop. If this one was going exactly twice the speed of that one, which I obviously could not replicate with my arms. So, use it as a feature. Me, that one kind of zippy, a little slower. They come together. This one wins out, because this guy must not be going twice as fast as that one. That's true. If I go a little faster, and if you go faster yet, if I can have this guy going faster than 2V, you can get it to go that way. But notice it's slow, so it wasn't much faster than 2V. Does that make sense? And the air's louder up here, so what? Say that again, please.
Oh, you were showing that on the map that V is 0, but V is not 0 in the experiment.
Correct, and I just justified why. Because the experiment didn't work. Remember, I got over here from the spring and stopped moving? Something messed it up. So I was trying to reproduce, making this one go twice as fast as this one. I got lucky in one of these just now. So in the experiment, this guy should be going 2V, and this guy V. That's what I couldn't match exactly. If I try, not close, but no cigar. There. I know this guy was going 2V and that guy V because they did stop afterwards. You follow this? Piece of putty being 1 unit, homework problem. So we have a little piece of putty running into a big bowling ball. This is not moving. And this is, right? Oh, big. Okay, then what? It hits and sticks. Is that an elastic or inelastic collision? Inelastic. This is inelastic. If they bounce, it's elastic. Continue. The momentum after. Okay, let's see what the momentum was before. That this has 1 unit of momentum? Okay. Well, that means you take its mass and its velocity, that's its momentum. It's calling that 1 unit of momentum. What's this guy's momentum initially? 0. Do you see that? He's not moving. His inertia is not in motion. So yeah, his momentum is 0. So the total momentum before the collision is 1 unit. What's the total after? It's got to be 1. When they stick, we'll now have big M, little m, and so you have big M plus little m at some final velocity, but I know that's got to equal 1 because conservation of momentum dictates it. So if I know its masses, and I know that incoming speed, I could figure out how fast they're going afterwards, couldn't I? Yes, for momentum, it doesn't necessarily have to mean it has to add up to 0. The total does not have to be 0. I think those cases are a little simpler, so I'm starting with those. But no, and here's a case. The total momentum before the collision is not 0. We're going to have this guy going faster. Too fast. Super slow. Total momentum before is not 0. So the total momentum afterwards won't be 0 either, but it'll be the same value. And it's still the same total. It's still the same total. It's still the same total. It's still. The total doesn't change. The individual ones might as they transfer momentum between each other, but between the system, the total net has to stay the same. Ideally, until it goes ka-chunk and, okay, some energy just left the system, and that's what we're getting up to. Energy is not always conserved in inelastic collisions. Inelastic. Because some of that energy gets transformed out of the system. Heat is one form that it will. I haven't gotten there yet, but we're starting to see it. So, did you follow that? Good. I think the book liked to do a fish one too. That was cute. Whee! Big fish, and he comes up on a little fish. Whoop. And when he eats him, will that be an elastic or inelastic? Inelastic, because afterwards their masses are together. But you play the same game. You got big M moving at some V, little m moving at, could be moving or not. It doesn't matter. So the total momentum before is whatever that equals. So I know the total has to stay that after the collision. We'll simplify. Okay. So again, though, they're together at some final velocity, and that's got to equal whatever it was. If it helps you, this is the same thing as, okay, the big fish is now moving at that velocity, but so is the little fish. This and this are the same thing, just written differently, however it works for you. Cool. Let's see. I about covered that. I'm sure some of you have started your homework. Why don't I take a couple queries, things that are bothering you? You got something?
I have one that is
Okay, yeah, I'll save that one then. But yeah, momentum stuff. Any of those bugging you that you're looking at and doesn't seem like I've covered it well enough for you?
Just this question before, it just says impulse-momentum relationship is a direct result of, is the different Newton's law?
Impulse and in which?
Impulse and momentum.
Impulse and momentum, yeah, they're a direct result of one of Newton's laws.
The second one, I think. But I know that you've gone over like how to do that math equation, like how to get that before. Like, I just wondering if you got things like
Yeah. The bottom of page 85 is exactly what I did. It's a footnote on page 85 for reference. But the gist was, so relating impulse and momentum. We start with Newton's second law. A force produces an acceleration. Acceleration is directly proportional to force, inversely proportional to mass. What is acceleration? It's a change in velocity over time. So we did some algebra looking stuff. Cross multiply. I'm going to multiply both sides by m and t to get them out of the denominator. If I multiply this side by m and t, the m's cancel and you're left with a t on this side. So it's like those go away and you're left. And on this side, the t's go away. And you got impulse is a change in momentum. I want to mention now there's room here. Maybe this will help. To change the motion of an object, what do you need to do? I heard it. Apply a force. To change the momentum of an object. What do you need to do? Apply a force for a certain amount of time. It's not just the force. That changes the velocity, but not the momentum. You have to apply a force for a certain amount of time. So an impulse, force time, must be applied. Ditto marks. Must be, an impulse must be applied. Do you see that?
Okay, so in the second one, the objects already have to be moving.
No. Example. No momentum. His momentum still just got changed because a force was applied for a certain amount of time on him. So his momentum just needs to change. But he can be moving. Still was changed. It's a good point though. And we're going to get to, I don't expect you to understand it yet, but you can write it down if you want. To change the energy of something. Somebody's been reading ahead. Work must be applied. You can write that. To change the energy. And that's what we're getting into. Work is a force times a distance. And that's where the next chapter starts. What? Yeah, we're going to explain this more. But So we have just a force. We have a force for a certain amount of time, and you can apply a force, and if you include the distance that force moves something, we call that work. And that's going to create a change in its energy. The chapter 7 starts with, and it is a great story, I've always loved it, about Émilie du Châtelet. If you read that, it was a great love story. But she did. It was like Galileo. He's like, people are arguing over, is energy, I like how the book puts it, oomph. They didn't know what to call it yet. You know something's got oomph. This is probably what's bugged you a lot up to this point. So I'm hoping this chapter will resolve lots of things. Okay, you got a force. That's great. And then we got this momentum, because it's moving inertia. You know it's hard to stop. You know the cannon's going to recoil. And you know the longer barrel is going to recoil more. This thing we call oomph, energy. They weren't sure if it was proportional to mv. Dang it. Oomph. Is it proportional to mv or mv squared? And so good old Émilie du Châtelet was doing some reading, and remember some other guy did an experiment. She redid the experiment. Not like Galileo. Well, let's just go try it. And she found out that it's proportional to mv squared. And kinetic energy, this energy of motion, energy of motion, is equal exactly, here's some proportionality constant, 1/2 mv squared. That's the kinetic energy of something moving. You see that if it's not moving, it has no kinetic energy. We're going to talk about different forms of energy. But that's kind of what a lot of people thought of when they were thinking of oomph back then. And it was great. She just dropped balls from certain heights into clay. I like using Play-Doh now myself. And the amount of dent, the depth of it, she could just measure. The higher up she went, she knew how fast it was going. We did that. You can just, we know the acceleration due to gravity, and we know how long it took, or we can time it, or we can measure it. And we can figure out how fast it's going right before it hits. And then it applies a force for a certain amount of time, transfers some energy into the Play-Doh, and it dents it, it deforms it, does work on it. You do work on something, you change its energy. And she could measure the divots. A lot like we measured the spacing between those two vehicles, the constant velocity little buggy and the fan cart. One went at a constant velocity, one accelerated. And the spacing between the positions at given time intervals told us that when something accelerates, you can see the distance get larger and larger. It's not linear. It's not a direct relationship, but it was actually related to the square. We didn't have to figure that out, but I told you that. She did the same thing. Simple, beautiful, and the debate was over. I loved it. That's the way to do things. So, work is one of those, unfortunately, that has a connotation in physics that seems a little different than in the everyday world. I like to call work as the effort applied to something, effort exerted on something. I can't emphasize the on something enough. That will cause that something to change its energy, or at least transform it, displace it. That's why I wrote this. This is how you should think of work. When you apply it to something, it causes that something to change its energy. Don't think of an object as having work. You can think of it as having energy, potential to do something. But don't think of it as having work. Work is a way to get energy from one thing to another. When we have collisions, energy is being transferred also. We just haven't discussed that yet. Does that make sense? Some people like noting the comparison too, that this is a force for how long. The book mentioned this, so I want to. Force for how long? Force for how long? But they're referring to distance this time. And this force has to be applied in the direction it's moving. That's the force you want to consider. Example. If I want to make this door rotate, I apply a force on it perpendicular to it because it swings. So I measure that force. Hello! And it moved this far. Force times distance, that's the work I did on it. But if I push on it this way, or this way, it doesn't move because my force isn't applied in the direction it's free to move. There is no displacement. It moves no distance in the direction I'm pushing. So we would say I did no work on the door. That's very important. If I'm pushing on the wall, then I'll get to you. Am I doing work? And see, you guys catch me every time I say it like that because that's in physics incomplete. Am I doing work? Because technically, am I doing work on the wall? No, because I'm not making it move. Well, at least that we can see, so for all practical purposes. I am doing work, as the book explains. My muscles are exerting forces and contracting and they're moving my muscles a little bit. So there's work inside, but I'm not doing any work on the wall. Okay.
What is the correlation between energy and force?
What's the relationship between energy and force? Essentially, that's your connection. This work, to change something's energy, you have to apply work, which means you need to exert a force on it to make it move. Later in the chapter, but we're there now, is the work energy theorem. And it says if you apply work on something, then you just changed its energy. And the amount of work that you exerted on it, ideally, there's going to be a change in energy. Yeah, I'll go back with ideal, and then I'll specify. All the work you do on something will cause it to change its energy. But we know in real life, sometimes all that change doesn't always go into just speeding something up. So if I push on this, I exerted a force on it for a certain distance, so I just did work on the block. I just caused it to have a change in energy. Its kinetic energy initially was 0 because it wasn't moving. I just got it up to a certain speed. It now has kinetic energy, so I changed its energy. But sometimes you can... The work I'm doing is now going into changing its kinetic energy as well as heat. The force of friction is converting some of that energy and transforming it into heat, leaving our system. If we account for that as well, then total energy is always conserved. And that's the conservation of energy statement in chapter 7. Just like momentum. Total momentum is always conserved if you consider everything. Total energy is always conserved if you consider everything, the whole system. So, example. Go back to this one. This is what type of collision? Elastic. So this guy has 1/2 mv squared. This guy has 1/2 mv squared, roughly. So when they come together, they can transfer some of their energy to the other one. And ideally, because we've tried to eliminate friction and they're just rebounding, that should be true. The total is conserved. The total energy between them is the total after. That one should make sense. It's the inelastic. Energy, kinetic. They combine. In an inelastic collision, kinetic energy appears to not be conserved. Because, wait, they're not moving anymore. Hope you can see that they're going to balance out. Some of the energy, kinetic energy that they had, energy of motion, gets transformed into heat, or sound is a form of energy. If I don't have the air on, well, where does kinetic energy go? It had kinetic energy. I push it. It's moving. It's got kinetic energy, and then it stops. That's because frictional force is acting on it while it's sliding, and friction is doing work on on the glider, which changes its energy. And so that kinetic energy I gave it, it just took away. Kinetic energy. So it looks like kinetic energy wasn't conserved. And kinetic energy wasn't. But do you see that the total energy is conserved? If it now has no kinetic energy, that energy had to go somewhere. It went into other forms. And if we could calculate those, it'd still be the total it had before. So in an inelastic collision, kinetic energy isn't conserved. Total energy is.
Okay, here's my question. Where is the conservation of energy when the apple on the tree that has potential energy falls to kinetic energy? Where, obviously it must go into the ground. Where is,
Great question. So she's like, so where does the energy, apple's on a tree and it falls. It's got potential and it falls. It starts moving, so it gains kinetic energy, but then it hits the ground and it all goes away. Well, I'm going to save that one for next lecture. It is called potential energy, and we're going to discuss that one specifically, between potential and kinetic. It likes to transform a lot between the two. And we're going to do some examples. But there are other forms of energy that your book does a great job of explaining. Kinetic is the one that we often deal with a lot of times, or is more conspicuous because it's the energy of motion. And I wanted to give you that as you're working on your homework because it probably helps you more. There is heat when it hits the ground. It might not be much, but it will. Anytime things smack together into form, there can be some heat involved.